Hi, this is Dr. John Bergdorf. In this video, I'd like to show a quick example of solving a linear equation in one variable that contains fractions. Here's an example of what I'm talking about. As you can see, this equation has one variable only, but there are fractions. Now, we can always work with the fractions as they are, but most people are not terribly comfortable with doing so. Fractions are not always our friends. So I have this idea that I want to show you that will help immensely. And the idea simply is to multiply both sides of the equation by the least common multiple of all the fractions in the equation. So we are not going to combine the fractions, but we're going to think about what the least common multiple would be as if we were going to add them. So we're going to need to think about and look for the least common multiple of all the denominators that you see in any of the fractions anywhere in that equation. Multiple is like skip counting. The multiples of 3 are 3, 6, 9, 12. The multiples of 4 are 4, 8, 12. The multiples of 2 are 2, 4, 6, 8, 10, 12. And as you can see in all those lists of multiples, the first one that I come to that is on every list is 12. So we believe that we ought to be able to solve this equation if we multiply both sides by 12. Let's see how that works. So I'm going to take the equation and I'm going to write it like this. So I'm going to multiply the left side by 12, like that, and I'm going to multiply the right side by 12. Whoops, I'm trying to stay color coordinated here. So let me change that back to blue. X over 2 minus 1 times 12. I can now use the distributive law to distribute the 12 across the parentheses on the left, which would give me 12, and let's think of that as 12 over 1 times 2x over 3 minus 12 over 1 times x plus 2. I'm going to put the parentheses in the numerator just so I remember that that entire numerator is together as a unit. And on the other side, also distributing across the 12, we will have, 12 over 1 times x over 2, and 12 over 1 times 1. And for 12, since there's no fraction in that term, let's just call it 12. Now, why on earth would we do this? The next step will show you why this is so important. As you look at the various products of fractions, say right here, the 12 over 1 times the 2x over 3, you will notice that the 3 in the denominator can divide into the 12 in the numerator 4 times, so that that product there is just 4 times 2x, which, let's go ahead and write that down. We don't need to, we can save time later. 4 times 2x over 1, so don't worry about the 1, minus, and then in the second grouping, the 4 divides into the 12 3 times, and we have 3 times x plus 2, and all over 1, but we don't have to write the over 1. On the other side of the equation, 2 divides into 12, and that gives me 6x, and then 1 times 12 is 12. And that is just so much simpler looking than where we started. That, in fact, is the point of multiplying both sides by the least common multiple of all the denominators. Let's turn the page and we'll continue from here. So I copied the question over again from where we are at the moment, just so we can continue from this point. As you can see, this is looking a lot simpler at this point. 4 times 2x is 8x. This 3 can again be distributed so that you would have minus 3x minus 6, that's the 3 times 2, equals 6x minus 12. Combining like terms, we have 5x minus 6 equals 6x minus 12. And at this point, we can gather all terms that involve x on one side of the equation and all terms that do not have x on the other side. Whatever operation we perform on one side of the equation, as long as we do the same operation on the other side, we are keeping the equation balanced. I noticed, for example, that it would be very simple to subtract 5x from both sides so that on the left, the 5x minus 5x will give me 0. And on the right, I can simply combine the two x terms into a single x. So 5x minus 5x gives you a 0. You get negative 6 equals x minus 12. And then to isolate the x completely, to get the x by itself, using that same idea of balance, I could add 12 to both sides. Minus 6 plus 12 equals x minus 12 plus 12. Same operation on both sides of the equation, keeps it balanced, leaves the solution unchanged. On the left side, you'll see that you get a 6, and on the right side, you get an x. Once we've solved for x, once we've isolated the x, then that value is the solution to our equation. And if we want to write that as a solution set, it would be the set containing 6. So I hope that's very helpful. Before we leave, this is always optional, but it sometimes is a good idea to check whether the solution is correct. This is the equation the way it was originally written, and as you can see, I've highlighted that our solution set contains the number 6. We could substitute 6 for all the values of x in here and see if this does simplify correctly. So we would have, if we do that, 2 times 6 over 3 minus, and then inside the fraction here, 6 plus 2 over 4. And what I'm going to do is put an question mark over the equal sign because I'm wondering, is this going to be equal? And on the other side of the equation, I'll write 6 over 2, substituting the 6, minus 1. And now let's simplify everything as best we can. 2 times 6 is 12, so we have 12 over 3. 6 plus 2 is 8, so we have 8 over 4. And I'm going to leave this for just a minute. It'll be more dramatic if we simplify all the fractions at once. Again, we're wondering, does that indeed make that equal? 12 over 3 is 4. 8 divided by 4 is 2. 6 divided by 2 is 3. Is it true that 4 minus 2 equals 3 minus 1? Yes, because this side, the left side would be 2, and the right side would be 2. And that checks, and we have verified that that is the solution. Thank you very much.